Welcome to Flow Simulation for the Design Engineer. Last time we discussed flow simulation for beginners, where we showed that flow simulation is not just applicable to those interested in modelling whole aircraft, but is now used in many industries and across many diverse applications. Here we see some examples. We discussed the various terminology used in flow simulation and some of the steps to success that a user should consider when setting up their model. Is the flow internal or external? Is it steady state or transitory? Is heat transfer important? And so on. Today we will take this one step further and show how, rather than flow simulation being the remit of specialists, it becomes hugely advantageous to use these techniques early in the design process. One of the roles of the designer or design engineer is to be creative with their solutions and to work on the ever-present balance between product functionality and cost. This is best achieved by making decisions early in the design process, and as such a designer needs tools to allow this. Let us take a typical example from the electronics industry. With electronics in confined spaces, heating is always a problem, and keeping components cool is a key element of the design. A properly cooled component will aid performance, increase lifespan, thereby reducing maintenance costs, and ultimately increase customer satisfaction. But conversely, if this is achieved at the expense of increased component costs or increased noise levels, then perhaps it is not so desirable. What is the solution? Well, this will vary for every product, and so a typical designer will need to be able to compare multiple designs to balance these competing forces for their specific problem. In our example, the following questions may arise. Will one fan provide the necessary cooling to protect the components? What is the effect of positioning the fan in different locations? If one fan is not sufficient, will two fans do the job? And what will be the cost increase per unit? What if we change the heatsink design to try to improve the CPU cooling? And if we find a number of solutions, what combination of fans and heatsinks will produce the best results? What we know for certain is that our CPUs must not exceed a temperature of 100 degrees C, as this is the upper range of their operating temperature. Let's see how we might approach this problem using SolidWorks Flow Simulation. Firstly, we need to set up the basic problem, and we can achieve this with the help of the Flow Simulation wizard, which will prompt us to define the major inputs to the model. The first prompt asks us to give the simulation a name, and also lets us identify which model configuration we are testing. So for example, here we are using a single fan model with a fan located in the middle of the CPUs. Although by choosing a different configuration, we can apply the same flow study to a different set of components for a direct comparison. This is the first benefit of performing simulation studies in an integrated CAD environment. Next, we define the unit system we wish to work in, and then the physical flow phenomenon that are important to us. For this kind of application, the flow will be internal to our model. We will choose to include the effects of gravity on our gas flow, and because our focus is to understand the cooling effect on our model, we should include heat conduction in solids. This will automatically consider the transfer of heat in the solid parts that come into contact with the fluid flow. Next, we will define the principal fluid in our system, which is going to be air. And because we've asked to include solids in our study, we must tell the simulation what solid material to consider. Let's pick an insulator as default. When we come to the initial conditions option, a tip to reducing the solution time is to set the pressure and the temperature of the air and the temperature of the solids as close to the assumed solution as possible, since it will need less effort to converge to a solution. Here we will accept the default atmospheric pressure and room temperature. And finally, we consider refining the solution around areas of our model that may have small gaps and thin wall components which are surrounded by fluid. In our model, we don't really need to worry about these kinds of features, but if we had, say, a tiny nozzle through which our fluid passes, or a thin baffle held in the flow stream, then we can highlight their relative dimensions to make sure these fine features are properly considered. Accepting our entries in the wizard then tells SolidWorks Flow to set up the model as we have defined with the information given so far. As you can see, a computational domain is constructed that fully contains the model, and we can hide this to make our view clearer. In essence, all we have to do to complete a basic setup from here is to define where and how our fluid will flow into and out of our model. However, before we do this, we shall take the time to assign some further detail to our model. For example, in our wizard we define the solid components to be made of insulating material, but this is merely a default. We can now define alternative materials to some components, leaving the remaining items the standard insulating material. So, by inserting a solid material, we can pick our end plates and define their properties as stainless steel. Similarly, we might define the transformers to be made of copper, the chips and small capacitors to be made of silicon, the PCB to be made of PCB 4-layer board, and the heat sinks on large capacitors to be made of aluminium. Next, we need to define how the air will enter our model and exit, and for this purpose we have two inlet vents at one end of the enclosure and a fan at the other end which sucks the air out of the enclosure. For internal studies in SolidWorks Flow Simulation, we must ensure that the model is fully closed, and so our inlets and outlets need to be blanked off by lids on which we define the boundary flow. SolidWorks Flow Simulation has automatic and manual methods of creating lids, and it is on the internal face of the lids that the boundary conditions are defined. So for example here we can apply normal environmental pressure to the two inlet vents, since these are assumed to be open to the normal ambient room. The same process of using a boundary face of a lid is used for the fan. However, rather than specifying atmospheric pressure, we want to suck air through this face and back out into the room. SolidWorks Flow Simulation allows us to select predefined fans from the built-in engineering database. So here we will choose an external outlet DC fan for our application. Now, remembering that the reason for a fan is to help remove heat from the enclosure, we must ensure that we define the heat emitting component in our model. For example, we can insert a volume source to make the CPUs generate 10 watts of electrical power. Similarly, we have set up heat sources for the large capacitor, medium capacitors and the transformers. Now that the flow test is set up, we should consider what we would like to measure from this test to see if our present design is suitable. Seeing as the major use of cooling fans is to prevent the internal components from overheating, we can set up a goal to measure the maximum temperature in the two CPUs. There are two things to note about goals. Firstly, defining a goal helps to identify the results of interest and extract them in a simple way post-calculation. Secondly, the creation of a goal also allows us to use this parameter in the convergence of the solution, so the solution is attained quicker. Perhaps a lesser known advantage is that these goals can also be monitored graphically during the solution process, so that on long runs it is easy to see if your model is wrong in some way, allowing you to cancel the run and save valuable time. So now we have completed the setup of the materials involved, the inlet and outlet conditions and the heat sources. It is now time to run the model. Once the flow test has been run, we are in a position to look at the results. To check the temperature of the CPUs, we can take advantage of the goals that we set earlier on by reporting the max temperature of the CPUs directly in Excel. Here we see that the maximum temperature in the CPUs is well over the desired 100 degrees C, and so some design change is clearly needed. We can also use SolidWorks Flow Simulation to demonstrate the flow trajectories, which will indicate how the air is drawn across the enclosure, cooling the various components along the way. Typically, this aids us in placing the various parts to obtain the maximum cooling effect, and is often helpful in indicating areas of flow recirculation or stagnation in systems. With a negative result from our first iteration, we clearly need to make a design change. Since SolidWorks Flow Simulation is integrated seamlessly within the CAD environment, this couldn't be easier. By using SolidWorks configurations, a number of design variants can be created based on the same dataset. Simply clone the existing project, choosing the configuration you want to test next, and rerun the test. In this way, we can produce a number of design variants and study them to see which is the best. So let's review the results. In our example here, we saw that the original heat sink and one fan design did not remove sufficient heat from the CPUs. Running the model again with a second fan acts to reduce the temperature further as expected, but the study still shows a maximum temperature exceeding 100 degrees C. At this point we cannot add more fans, so we might try a different heatsink design. Again, defining a different SolidWorks configuration where the heatsink is replaced by a circular pin sink. Running the study shows that we get another improvement. However, this is still not sufficient, only cooling our CPUs to 104 degrees. A final change to the heatsink design delivers the best cooling performance when using the straight vaned heatsink, leaving us with a much improved temperature of 93 degrees C. Now we are well under our target temperature, but we are using two fans. A final change in configuration back to the one fan design, but retaining the vaned heatsink, delivers a temperature limit around our target of 100 degrees C. And we have minimized parts, electrical demand and noise in our overall design. So we have finally found our optimum design configuration for this problem, a combination of a straight vaned heatsink and one fan. However, what have we learnt along the way? We have seen that the flow simulation tools available in SolidWorks are an extension to the SolidWorks environment, making it easy to use, familiar to the designer, and integrated with the existing powerful SolidWorks tools. SolidWorks Flow Simulation helps you to design better products. By performing multiple what-if scenarios, a designer can quickly test all their ideas to find out which one is the best. And finally, SolidWorks Flow Simulation offers a complete simulation solution so that all of your company's design challenges can be answered. If you would like to know more about flow simulation from SolidWorks, please visit the SolidWorks website. Thank you very much for your time. I hope you found it informative. If you have any further questions, please feel free to email me at this address.